Hello everyone, myself Bharat Dav. I am a doctoral student in the Department of Chemical Engineering, IIT Kanpur, and I welcome you all to this fifth lecture of thermodynamics. So, in the last class, in lecture 4, we have seen about the definition of work, and also we have derived an expression for work done in a irreversible process. Further, we have also studied about what is the definition of irreversible work and what is a reversible work. So here, the work, if it is a continuous process, then the work done is called as reversible work, whereas if the work done is sudden, that is of an irreversible process, then the work is called as an irreversible work. So in today's class, that is in fifth lecture, we are going to derive an expression for reversible work calculation for an isothermal process. Further, we are also going to study about what is free expansion and work done in free expansion, and then further we also dive deeper into law of conservation of energy, that is the first law of thermodynamics, and derives up expression for work done for various other processes such as adiabatic process, isothermal process, so on and so forth. Okay, so let us start. So this is going to be fifth lecture. Thermodynamics. Okay, so the first topic which we are going to see is, so in the previous class we have studied about reversible work. So let us write the definition of that thing again. So a process or change is said to be reversible, if it is brought out in such a way that the process could at any point or any moment be reversed by an infinitesimal change, right? This is called as a reversible process. This is called as a reversible process. Okay, the second statement would be a reversible process proceeds proceeds a reversible process proceeds infinitesimally slowly by a series of equilibrium states, such that the system and the surroundings are always in near equilibrium with each other, right? And the processes which are not reversible are called irreversible process. Irreversible processes, right? So it may be noted that we can also relate work to internal pressure of the system under reversible conditions, right? So it is to be noted that we can also relate work to the internal pressure of the system under reversible conditions if volume changes from let's say example V1 to V2. It may be expressed as, in that case, W reversible is nothing but integral volume is going to change from V1 to V2, and this is going to be P external into change into volume, right? Hence we can write W reversible is nothing but minus integral V1 to V2 P external multiplied by dV, which means by W reversible is nothing but minus integral V1 to V2 P in plus minus dP dV, right? Which is nothing but minus integral V1 to V2 P in dV, right? Plus minus, sorry, so this is going to be inside the integral plus minus dP into dV. Now we know that both dP and dV are infinitesimally small, so that dP into dV is even smaller, is doubly infinitesimal. And hence can be neglected. Right? Therefore, we can write as W reversible is nothing but integral V1 to V2 P in into dV. Right? Now, for an ideal gas, we know that PV is nothing but nRT, which implies pressure is nothing but nRT by V. Therefore, substituting this, from, let's say for example, call this as equation A, equation B, right? Right, this is equation A and this is equation B. So from equation A and B, we get W reversible is nothing but minus integral V1 to V2 P internal is nothing but nRT by V into dV, right? Which what this implies W reversible is nothing but integral V1 to V2 for let us so nRT is going to be constant, nRT minus integral v1 to v2 dv by v, which implies W reversible is nothing but minus nRT into ln v, where v is going to change from v1 to v2. Accounting for the negative signs, this is going to be ln v1 by v2, right? So this is one of the expression which gives work done, right? So if you want to change this ln to log, this is going to be 2.30 t nRT ln v1 by v2 or minus 2.303 nRT ln v2 by v1, which is nothing but nRT minus ln v2 by v1, right? So these are all expressions which corresponds to a single v reversible, right? So hence what we can write is, at constant v temperature, what we have p1 v1 is nothing but p2 v2, right? Or v2 by v1 is nothing but p1 by p2. Therefore W reversible in that case is minus 2.303 nRT log of p1 by p2. So this is also one of the important expression, right? Now let us consider a case of free expansion. So in free expansion, what we have, let's say for example we have a container. Let us move on to the next page. So free expansion, so for example consider a container, right? And let us consider that okay, so let's consider gas is there, inside pressure is P internal and outside pressure is P external, right? And for example consider that P internal is greater than P external. Now if we do P external is equal to 0, then what is going to happen is, there is only one pressure which is going to, only one force which is going to apply in this case, and there is no opposing force, right? So then no opposing force, therefore work done is going to be 0, because there is no external pressure upon which gas has to work, right? So let us write this down. So free expansion, so expansion of a gas in vacuum, expansion of a gas in vacuum, that is when P external is going to be 0, is called as free expansion, right? It may be noted that no work is done during free expansion of an ideal gas, whether the process is reversible or irreversible, right? So this is a very important thing which we have to remember. In addition to these two modes, radiant energy and electrical energy are also modes of transfer of energy between the system and surrounding. Right. So now let us look into very important aspect, which is units of heat and work. Right. So the heat exchanges are measured in calories. So let us write this down. The heat exchanges, the heat changes are measured in calories, and the unit for that, abbreviation for that is cal, kilocalorie, which is kcal, joules, which is denoted as capital J, or kilojoules, which is kilojoule. Right, and these are related as 1 calorie is going to be 4.184 joule, and 1 kilocalorie is going to be 4.184 kilojoule. Okay, then the SI unit of heat is joule or kilojoules. Right. Work is measured in terms of ergs or joules. Right, and 1 joule is nothing but going to be 1 joule is 10 raised to power 7 ergs. Right, and the SI unit of work is joule. Right, and also additionally we have 1 joule is nothing but 1 Newton meter, which is nothing but 1 kg meter square second to the power minus 2. Right. So how is that possible? We know that work is going to be nothing but force into distance, which is nothing but Newton into meter, which is Newton meter, which is nothing but 1 joule. Right. Then force is going to be mass into acceleration. Right, and then hence work is going to be nothing but mass, which is kg, multiplied by meter per second square, which is multiplied. Right, so this is going to be force, right, multiplied by distance, which is m, which implies that work is going to be kg meter square by second square, which is nothing but kg meter to second minus 2. Right, one joule is nothing but 1 kg meter square second to the power minus 2. Right. The next topic which we are going to study is the law of conservation of energy, which is also known as the first law of thermodynamics. Law of conservation of energy, which is nothing but first law of thermodynamics. First law of thermodynamics. Right. So the total energy of the universe is present either as a kinetic energy or as a potential energy during a physical or chemical change the energy may be converted from one form to another. Like for an example, when we throw a stone or a ball from, let's say for example, 5th floor of the building, so initially it has zero kinetic energy and a potential energy equal to mgh, and assuming that there is no air resistance, when we throw the ball continuously gains up energy in the form of kinetic energy and loses the potential energy, and as soon as it hits the surface of the earth, we say that it has zero potential energy and kinetic energy, which is going to be equal to its initial potential energy. Hence there is no loss of energy but only conversion from one form of the another. For like this we can also say similar things for the entire universe. Right. So for example, the water stored in a dam possesses potential energy by virtue of its height. When the water is allowed to fall, its potential energy changes into kinetic energy. Due to its kinetic energy, the falling water can rotate the turbines and produces electricity. Thus, the potential energy of the water gets converted into kinetic energy. In other words, the total energy remains constant when the body changes its position, though one form of energy may be converted into another. This leads to an important conclusion known as the conservation of energy and has been put forth in the form of a law known as first law of thermodynamics, right? So what is the first law of thermodynamics? So let us write this down. So first law of thermodynamics, right? It says that energy can neither be created nor destroyed, although it can be converted from one form into another. One form into another. This law holds good in chemical reactions also, right? Energy may be absorbed or evolved in chemical reaction, but the total energy of the reacting system and the surrounding remains constant, right? So let us write this down as well. This is very important statement. This law holds good in chemical reactions also. In chemical reactions also, their energy may be absorbed or evolved in chemical reaction, but total energy of the reacting system total energy of the reacting system and the surroundings remains same, right? This law has been stated in several other ways, but the basic idea remains the same, that is conservation of energy, right? So we can write this as other statements of first law. So these are, for example, first one could be the total energy of the universe remains constant. The total energy of the universe remains constant, right? Number 2, the energy of the system that is isolated from its surrounding, that is isolated system, is constant, right? The energy of the system the energy of the system that is isolated from its surrounding that is isolated system is constant, right? So let us now study justification for the first law of thermodynamics. Let us move on to the next topic. Next page. Justification for the first law of thermodynamics, for the first law of thermodynamics, right? The first law of thermodynamics has no theoretical proof. It is a law based on human experience and has not yet been violated, right? This is very important. So there is no proof for this first law. The first law of thermodynamics has no theoretical proof. Right? It is based on human experience and has not yet been violated. Right? So it is based on human experience and has not yet been violated. Not yet been violated, right? It is right. The following observation justify the validity of this law, right? Let us write this down. The following observations justify the validity of this law. Validity of this law. For example, for the first one is, it is not possible to construct a perpetual machine which can do work without expenditure of energy. If the law were true, it would have been possible to construct such a machine, right? So we will study what is a perpetual machine. So in short summary, perpetual machine is nothing but a machine in which total heat can be converted into work and total work input can be converted into heat, right? So we will study about it in our in subsequent classes. So for now, it is just suffice to note this statement down. So it is not possible to construct a perpetual machine which can do work without the expenditure of energy, without the expenditure of energy. If the law were true, if the law were not true, then it would have been possible to construct such a machine. Right? The second point is, Joule in 1850 conducted a large number of experiments regarding the conversion of work into heat energy. He concluded that for every 4.183 joule of work done on the system, 1 calorie of heat is produced. He also pointed out that the same amount of work done always produces same amount of heat irrespective of how the work is done. So James Joule in 1850 conducted a large number of experiments regarding the conversion of work into heat energy He concluded that for every 4.183 joule of work done on the system, 1 calorie of heat is produced. He also pointed out that the same amount of work done always produces same amount of heat irrespective of how the work is done. Right. So the third point is energy is conserved in chemical reactions also. For example, the electrical energy equivalent to 286.4 kilojoule per mole of energy is consumed when 1 mole of water decomposes into gaseous hydrogen and oxygen. On the other hand, the same amount of energy in the form of heat is liberated when 1 mole of liquid water is produced from gases oxygen and hydrogen. These examples testify that the energy is always conserved, though it may change its form. Right? So energy is conserved in chemical reactions also. For example, the electrical energy equivalent to 286.4 kilojoule per mole of energy is consumed when 1 mole of water decomposes into gaseous hydrogen and oxygen. Right? On the other hand, the same amount of energy in the form of heat is liberated when 1 mole of liquid water, 1 mole of liquid water is produced from gases hydrogen and oxygen. So in a chemical reaction way, I can write water in liquid plus 286.4 kilojoule of energy gives me hydrogen in the form of gas plus half mole of O2 in the form of gas, right? So if I were to carry out opposite reaction in which 1 mole of hydrogen in gaseous phase reacts with 1 mole of half a mole of water, half mole of oxygen in gaseous phase gives rise to liquid water plus 286.4 kilojoule of energy, right? So these examples justify that energy is always conserved, though it may change its form. It may change its form, right? So the next topic which we are going to see is the mathematical expression for first law of thermodynamics, right? The mathematical expression for first law of thermodynamics, right? So let us consider a general case in which a change of state is brought by doing work and by transfer of heat, right? So the internal energy of the system can be changed in two ways: by allowing the heat to flow into the system or out of the system, or by doing work on the system or by the system, right? So let us write this down. So let us consider a general case in which a change of state is brought, both by doing work, and by transfer of heat. The internal energy of a system can be changed in two ways. First way is by allowing heat to flow, into the system or out of the system. And the other one is by doing work on the system, by doing work on the system or by the system. Right? So now let us consider a system whose internal energy is U1, right? So let us consider a system whose internal energy is U1, whose internal energy is U1. Now if the system absorbs the system absorbs Q amount of it, then the internal energy of the system increases, then the internal energy of the system increases and becomes U1 plus Q, right? Now if work in amount of W is done on the system, then its internal energy further increases and becomes U2. Thus what we can write is U2 is nothing but U1 plus Q plus W. Therefore U2 minus U1 is Q plus W. Therefore we can write change in internal energy is nothing but Q plus W, right? So hence that is change in internal energy is nothing but heat added to the system plus work done on the system. The above expression is a mathematical statement for first law of thermodynamics. Now if a system does work in amount W on the surroundings, its internal energy decreases. Its internal energy decreases. In this case, work is taken as negative. That is W is nothing but minus W. Now if Q is the amount of heat added to the system, Q is the amount of heat added to the system, and W is the work done by the system, and W is the work done by the system, then in that case I can write delta U is nothing but Q plus minus W, which is nothing but Q minus W. Therefore change in internal energy is nothing but heat added to the system, heat added to the system minus work done by the system. Work done by the system. Right? The above relationship is between internal energy and work is also another mathematical statement for first law of thermodynamics. Right? So in this class, what we have studied? In this class, we have derived expression for work done for an isothermal process. Further, we have also seen that the work done is equal to 0 for a reversible, for a free expansion process. Further, we have also seen the units of heat and work. And additionally, we have also seen the law of conservation of energy, which is nothing but first law of thermodynamics. We have given an statement for this, and then we have stated that there is no theoretical proof for this. However, there are certain cases, or there are in almost all the cases, the first law of thermodynamics has been found to be accurate, and we have elaborated this with the help of a couple of examples, and then at the end we have given a mathematical expression for first law of thermodynamics. So in the next class we are going to study the work done for different types of processes, and then also we are going to study about the sign convention for a heat and work for this first law of thermodynamics, and then if the time permits we'll also go into enthalpy and enthalpy change, which is nothing but another useful state function just like internal energy. So I thank you all for attending this class, and I hope to see you all again in the next class. Thank you. Hello everyone, I welcome you all to this sixth lecture of thermodynamics. My name is Varad Dau. I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in the previous class, we have seen about the law of conservation of energy, that is the first law of thermodynamics. We have seen how the can be quantified, and we have also seen the different sign conventions. That is when work is done on the system and heat is taken out of the system, and the other way around. And then we have finally arrived at this expression that change in internal energy is nothing but the sum of the heat and work done. Okay, so in present class we are going to elaborate onto this, and then we are going to study about various sign conventions which are used. Okay, so this is lecture 6, thermodynamics. Dynamics. Okay, the first topic. So we have seen that delta U is going to be Q plus minus W, right, where where the sign conventions, where the sign of Q and W depends on whether the heat or work is added or taken out of the system. Correct? So we are going to elaborate on it. This relationship about between the internal energy and heat is called as the first law of thermodynamics. So this is the first law of thermodynamics. Okay, first law of thermodynamics, right? So for example, when we substitute, W is nothing but PV, right? For example, we know that delta W is nothing but is equal to minus P external into delta V. Then delta U becomes what? Delta U is nothing but equal to Q minus P external into delta V. And if the process occurs at a constant volume, then what we can say is, if the process occurs at a constant volume, if the process occurs at a constant volume, then delta V is going to be 0. Therefore delta U is going to be nothing but Q. In that case we denote this by QV, right? The subscript V in QV indicates that the heat is supplied at a constant volume. Indicates that the heat is supplied at constant volume. It is supplied at constant volume, right? Thus, if a reaction is carried out at constant temperature and constant volume, then no work is done and the heat exchange with the surrounding is equal to the change in the internal energy. Thus, the change in internal energy of a reaction is equal to the heat evolved or absorbed during the reaction at constant temperature and volume conditions, right? So let us write this down, that if a reaction is carried out at a constant temperature, if this is the first point, the second point, if a reaction is carried out at constant temperature and constant volume, then no work is done and heat exchange with the surroundings is equal to the change in internal energy. Right? Thus the change in internal energy, which is nothing but delta U of a reaction is equal to heat evolved or absorbed during the reaction at constant temperature and constant volume. At constant temperature and constant volume, right? Therefore we can write that delta U is nothing but heat absorbed or evolved in a reaction at constant temperature temperature and volume. For let us move on to the next page. For isothermal changes in an ideal gas, right? For example, expansion into vacuum, expansion into vacuum at constant temperature, delta U is going to be 0. Why? Because W is going to be 0. Why? Because P external into delta V, which is nothing but 0 into delta V, because there is no pressure gradient in free expansion. This is 0 and there is no isothermal, right? That means there is no heat change, right? Joule experimentally found that Q is equals to 0, since U is a state function. Delta U is going to be 0 for all isothermal processes which are reversible as well as irreversible, right? That's the general expression, right? Thus the general expression which is delta U is nothing but Q plus W may be expressed for isothermal irreversible and reversible changes as Q is nothing but equal to minus W, which is nothing but P external into final volume minus initial volume, right? So this is for, so let me write this out with a different color. So for isothermal irreversible change, Q is nothing but minus W, which is Px into Vf minus Vi. For isothermal reversible change, Q is going to be equal to minus W, which is equal to nRT ln Vf by Vi, right? Or Q is going to be equal to 2.203 into nRT into log of Vf by Vi. Why we can write it? Because W is nothing but minus integral PdV, and for an ideal gas and reversible change we know that V is nothing but RT by P, right? So W is nothing but integral RT by V, RT by V, this is going to be, P is going to be RT by V, right? That means this is going to be VdV, and when you integrate this, that is what you get, right? For adiabatic change, for adiabatic process, we know that Q is going to be equal to 0, right? Hence delta U is going to be nothing but work of adiabatic, right? So these are very important results which one has to remember, right? One should be able to know, right? But however, while reminding this, one also has to remember that it should be noted that the first point which has to be noted is energy is a state function and delta U depends only on the initial and final state, whereas work and heat are not a state function. The values of Q and W depend upon the way in which the change is carried out. However, whatever may be the process, delta U is always equal to Q plus W, and therefore Q plus W is a state function, right? So energy is a state function and delta U depends only on the initial and final states, right? Whereas Q and W depend upon the way in which the change is carried out, right? However, whatever may be the process, delta U is always equal to Q plus W, and therefore Q plus W is also state function. It is very important, right? So Q individually is not a state function, right? Similarly, W on itself is not a state function, right? However, both when you consider a property which is a linear combination of both the work done and the heat exchange, then a new property emerges which is also called as, which we are also calling it as internal energy, and this internal energy however is a state function. So combination of two path functions is giving rise to a state function, right? Second point is, for ideal gas undergoing an isothermal change, the internal energy of the system does not change, right? That means delta U is equal to 0, right? This means that the heat absorbed by the system is equal to the negative of the work done on the system or equal to work done by the system, right? For an ideal gas undergoing an isothermal change, the internal energy of the system does not change, that is delta U is equal to 0. Then as per first law, 0 is nothing but Q plus W, implies Q is nothing but minus W or W is nothing but minus Q, right? This means that heat absorbed heat absorbed by the system is equal to the negative of the work done on the system or equal to work done by the system, right? The next topic which we are going to study is the sign conventions, right, which are very important. Sign conventions for heat and work. So it is very important to understand the sign conventions for Q and W. The sign of Q and W are related to the internal energy change. When Q or W are positive, it means that the energy has been supplied to the system as work or as a heat. The internal energy of the system in such cases increases. On the other hand, if W or Q is negative, it means that the energy has left the system as work or heat, and the internal energy of the system in such cases decreases. Right? So let us write this down. So for the first point, the signs of W and Q are related to the internal energy changes, right? When W or Q are positive, it means that energy has been supplied to the system, right? Energy has been supplied to the system, right, as work or heat, and in such cases the internal energy of the system increases, right? On the other hand, if W or Q is negative, it means that energy has left the system as work or heat, and in such cases the internal energy of the system decreases, right? So let us first try to illustrate this with the help of an example, right? So let us consider, right? So let us illustrate this with the help of an example. So let us go back to the new example. So let us illustrate this example with convention. If heat is absorbed by the system, then Q is positive, since there is increase in the energy of the system. But if the heat is evolved by the system, then Q is given a negative sign, since there is a loss of energy. For example, if we supply 25 kilojoule of heat energy to the system, we write Q as plus 25 kilojoule. But if same amount of heat is given out to the surroundings, we write Q as minus 25. When work is done on the system, W is positive, that is energy of the system increases, but if system does work on the surrounding, then W is negative, that is energy of the system decreases because work is done at the cost of energy. For example, if 15 kilojoule of energy is transferred to the system by doing work on the system, then we write W as plus 15 kilojoule. But if the system does 15 kilojoule of work on the surroundings, then we write W as minus 15 kilojoule, because the system has lost 15 kilojoule of energy, right? So in this way we can understand, right? Does anybody have any doubt? If not, then we'll move on to the next part of the presentation, next part of the class. Right? So first let us write this down, right? Sign convention, yes. So here only we write, right? For example, if heat is absorbed by the system, Q is positive, right? Since there is increase in energy, there is increase in energy of the system, right? But if heat is evolved by a system, then Q is given negative sign, right? For example, if we supply Q is equals to, if we supply 25 kilojoule of heat energy to the system, we write Q is equals to plus 25 kilojoule. But if same amount of heat is given out to the surroundings, we write Q is equals to minus 25 kilojoule, right? When work is done on the system, W is positive, right? That is energy of the system increases. But if system does work on the surroundings, W is negative, right? For example, if 15 kilojoule of energy is transferred to the system by doing to the system by doing work on the system, work on the system. We write W is equals to plus 15 kilojoule. But if the system does 15 kilojoule of work on the surroundings, we write W is equals to minus 15 kilojoule, because the system has lost 15 kilojoule of energy, right? So this full thing can be represented by following table, right? So heat absorbed by the system, in that case Q is going to be positive, right? Right. So let us write this down with the help of this. Heat absorbed by the system is going to be Q. In that case Q is going to be positive, that means plus Q. Heat evolved by the system in that case Q is going to be negative, right? Now if work is done on the system, in that case W is going to be positive, right? Now if work is done by the system, in that case W is going to be negative, okay, right? So this has to be encapsulated, right? Thus in general W and Q are positive if energy as work or heat enters the system and W and Q are negative if energy as work and heat leaves the system. Right? So the next topic which we are going to study is enthalpy and change of enthalpy, right? Change in enthalpy. So the next topic which we are going to study is enthalpy and enthalpy change, a useful state function, a useful state function. Right? The change in internal energy gives the heat change accompanying a chemical reaction at constant volume, right? Because we have seen that delta U was equal to QW when process is isochoric. So isochoric means delta V is equal to be 0. However, in laboratory, most of the chemical reactions are carried out at constant pressure rather than at constant volume. For example, all systems open to atmosphere are obviously at constant atmospheric pressure. When a chemical reaction takes place in an open atmosphere, there may be change in volume, but the pressure remains constant, which is nothing but equal to atmospheric pressure. To study the heat changes for reaction at constant pressure and at constant temperature, a new term called as enthalpy has been introduced. Right? Let us write this down. So, the change in internal energy, we know that the change in internal energy gives the heat change accompanying chemical reaction at constant volume. At constant volume, which is nothing but delta U is nothing but QV, right? However, in laboratory, most of the chemical reactions are carried out at constant atmospheric pressure. When a chemical reaction takes place, right? When a chemical reaction takes place in an open atmosphere, there may be changes in the volume. But the pressure remains constant. That is nothing but atmospheric pressure. To study the heat changes for reaction, reactions at constant pressure and at constant temperature a new term called enthalpy has been introduced. has been introduced. What we have learned? We have learned that internal energy can be expressed as delta U is going to be QP minus P delta V at constant temperature, right, where QP is the heat absorbed by the system, and minus P delta V represents the expansion work done by the system. Expansion work done by the system, right? So now let us represent initial state by subscript 1 and final state by 2, so that we have delta U is nothing but U2 minus U1, which is nothing but QP minus P into V2 minus V1, right? Upon rearranging, we get QP is going to be equal to U2 plus PU2 minus, sorry, this is not U, this is V, PV2 minus U1 minus plus P1 V1, right? So P into V1, right? So let us call this as expression 1 and this as expression 2. Now we can define another thermodynamic function, which is enthalpy, which is nothing but H, right, which is also called as heat content, as, so let us write this down, H is equals to U plus P into V. This is very important, and H is nothing but equal to U plus PV, right? So equation, equation 2 becomes QP is equal to H2 minus H1, which is nothing but delta H. So one very important thing which has to be remembered here is, although Q is a path dependent function, path dependent function. QP is independent of path. QP is independent of path. Right? So let me highlight this down. It is independent. Right? Let me write down independent of path, and let me use yellow color to highlight it. Right? Independent of path. Thus H is a state function. This is very important. This is also very important. Function. Right? It is a state function. Right? So it is a state function. Right? Thus delta H is independent of path, thus enthalpy of a system may be defined as follows. The sum of the internal energy and the product of its pressure and volume. Right? And hence we can write H is nothing but U plus PV. Right? Where H is nothing but enthalpy, U is the internal energy, P is the pressure, and V is the volume. Right? Enthalpy is also we can define it as a heat content. Of the system. Right? So in the present class we have studied about the sign conventions which have been used in the first law of thermodynamics, and the important thing is, if heat is added to the system or if work is done onto the system, then in that case we consider both heat and work as positive. However, if heat is removed from the system or work is done by the system, then in that case we consider both heat and work as negative quantities. And further we have also studied about the enthalpy and the usefulness of enthalpy and the need of enthalpy, and then we have also defined enthalpy, which is equal to nothing but U plus PV, and in that case we can also call enthalpy as the heat content of the system, and H is equal to nothing but U plus PV, where U represents the internal energy, P represents the pressure, and V represents the volume. So in the next class we are going to we are going to delve deeper into the change in enthalpy, and we are also going to study the significance of internal energy and enthalpy and the correlation between them using the first law of thermodynamics. Right? and then if the time permits, we'll also study about the how to calculate enthalpy change of a reaction using some solved examples, right? So I thank you all for attending this class, and I hope to see you all again in the next class. Thank you all. Hello everyone, I welcome you all to the seventh lecture of thermodynamics. So in the previous class we have seen about the sign conventions, different sign conventions which which should be used for work and heat while applying the first law of thermodynamics. We have seen that if heat is added into the system, then heat is taken as positive. If heat is taken out of the system, then heat is considered as negative. Whereas if work is done on the system, then the work is taken as positive, whereas if work is done by the system, then the work is taken as negative. Further, we have also seen the importance of enthalpy, and we have also defined enthalpy in terms of its internal energy and pressure volume, and then we have also defined the usefulness of this enthalpy, and we have defined that the sum of internal energy and the product of its pressure and volume is nothing but the internal enthalpy. We have also seen that this enthalpy is a state function, that is, it does not depend on the path, but it only depends on initial and final properties. And we have also seen that enthalpy is nothing but the heat content of the system. Okay, so in this class we are going to delve further, and then we are going to see about the change in enthalpy and its significance, and how does it relate to the first law of thermodynamics. Further, we are also going to study this change of enthalpy with respect to the chemical reactions. Okay, so let us start. This is lecture 7. Thermodynamics. Right. So every substance has a definite value of enthalpy in a particular state. Like internal energy, the absolute value of enthalpy cannot be measured. However, the change in enthalpy accompanying a process can be determined. Right? So, thus, for example, if we have a process, chemical reaction in which a reactant A is going to get converted into product B, then the change in enthalpy, which would be denoted as delta H, which would be nothing but the absolute enthalpy of the product minus absolute enthalpy of the reactant. Thus, the enthalpy change of a reaction is equal to the heat absorbed or evolved during a reaction at constant temperature and pressure. Right? So, let us write this down. Like every substance has a definite value of enthalpy, has a definite value of enthalpy in a particular state, like internal energy, the absolute value of enthalpy, the absolute value of enthalpy cannot be measured, right? However, the change in enthalpy change in enthalpy accompany accompanying a process can be determined. Thus, for a process Thus, for a process represented as is going to be the change in enthalpy may be expressed as delta H is going to be HB minus HA, where HA is the enthalpy of state A, HB is the enthalpy of state B, and delta H is the enthalpy change, right? For a chemical reaction, delta H can be given as difference between the enthalpies of the product and the reactants, that is delta H is going to be H products minus H reactants. Right, which is nothing but in the notation term is HP minus HR, where HP is enthalpy of products and HR is the enthalpy of reactants, and delta H enthalpy change. Right? If a reaction is carried out at constant temperature and constant pressure, the heat exchange by the system the heat exchange by the system with the surrounding that is equal to change in enthalpy. Thus, we can write as the enthalpy change of reaction is equal to the heat absorbed and or evolve during a reaction at constant temperature and pressure. At constant temperature and pressure. In symbolic terms, it is written as delta H equals to heat evolved or absorbed in a reaction at constant temperature and pressure. Constant temperature and pressure. It may be noted that the amount of heat exchange with the surrounding for a reaction at constant pressure is different from that exchange at constant volume. This can be easily understood. At constant pressure, the volume of the reacting system changes. If the volume increases, the system expands against the atmospheric pressure and energy is required for this expansion. Therefore, a part of energy will be used for the expansion. As a result, the amount of heat exchange at constant pressure would be less than the amount of heat exchange at constant volume. Right? Alternatively, if the system contracts at constant pressure, work is done on the system and the system absorbs some energy from the surrounding. Therefore, the amount of heat exchange at constant pressure is greater than that exchange at constant volume. So let us write this down. It may be noted that the amount of heat exchange with surrounding for a reaction at constant pressure. So what is this quantity? This is nothing but change in enthalpy, right? Because it is at constant pressure, right? At constant pressure. This is the thing but delta H is different from that exchange at constant volume. Now what is this thing? This is nothing but delta U, right? And temperature, right? This can be easily understood, right? For example, at constant pressure, the volume of the reacting system changes. The volume of the reacting system changes. If the volume increases, the system expands. Against the atmospheric pressure. And energy is required for the expansion. right? Therefore a part of the energy will be used for the expansion, will be used for the expansion, right? As a result, the amount of heat exchange, the amount of heat exchange at constant pressure, which is nothing but delta H, right? Would be less than at constant volume. Now what is that? This quantity is nothing but, we have already seen, this is delta U, right? Conversely, alternatively, if the system contracts, at constant pressure, work is done on the system, and the system absorbs some energy from the surrounding. Right? Therefore, the amount of heat exchange, at constant pressure is greater than that exchange at constant volume. Right? That is why delta H is always going to be greater than delta U. Right? Now, let us understand the significance of this thing. Right? Significance of, the next topic is significance of delta U and delta H and first law of thermodynamics. Right? The significance of delta U and delta H follows from the first law of thermodynamics. So according to the, let us use a black pen. So according to the first law, we know that delta U is nothing but U plus W. Now let let the change in volume during the process at constant pressure is delta V. So now let us consider, let the change in volume, let the change in volume during the process at constant P is delta V. Then work is referred to as pressure volume work, and it is given as P delta V, right? When a gas expands, work is done by the system, right, on the surroundings, and the work is minus P delta V, right? Therefore delta U becomes P minus P delta V, sorry, Q minus P delta V, right? Therefore Q is going to be nothing but delta U plus P delta V, right? So let us consider this as expression 1. Now if the process is carried out at constant volume, that is delta V is equals to 0, then we have Q is going to be nothing but delta U. Now the special condition for this thing, we are denoting this Q as QV is going to be equal to delta U, or delta U is going to be QV. Okay? This is also very important. So what we can understand from this is that the change in internal energy is equal to the heat absorbed evolved at constant volume and constant temperature. The change in internal energy is equal to heat absorbed or evolved at constant volume and constant temperature. Right? Now for example, let us go to the definition of enthalpy. Now we know that enthalpy is going to be nothing but U plus PV, right? Not change in enthalpy, only enthalpy. Therefore delta H is going to be delta of U plus PV, right? That is delta H is going to be delta U plus P delta V plus V delta P, right? Now, right, so this is, let us for example consider as expression 3, and if the process is carried out at constant pressure, then that means delta P is going to be equal to 0. Therefore delta H is going to be delta U plus P delta V, right? Now again, right, now we know that we know that delta U is nothing but U plus W, and if the work done during the process is expansion work, is only expansion work, then W is going to be what? Minus P delta V, right? And we already know that Q is nothing but delta U plus P delta V, right? Therefore what we get? We get delta U is going to be nothing but Q, right? Sorry, for example, we get, right, we get delta H. So delta U is going to be Q minus P delta V, right? And hence when we substitute, is going to be Q minus P delta V plus P delta V. Therefore delta H is going to be nothing but Q, and this special condition is what we are calling it as QP. Therefore call it as QP. Therefore delta H is nothing but QP, right, at constant pressure, right, where QP indicates the heat change has taken place at constant pressure. Therefore we can say that the enthalpy change is a measure of heat change evolved in bracket evolved or absorbed taking place during a process at constant pressure, right? Hence we can sum it up as Q at constant volume is going to be nothing but delta U, and Q at constant pressure is going to be delta H. This is very important thing which one has to remember, right? Now let us try to understand it. Go on to the next topic, next page, and try to understand the relationship between change in enthalpy and change in internal energy. Right? Yeah. So consider reaction. consider a reaction which is A going to B, an irreversible type of reaction. A going to B at constant, consider reaction A going to B at constant. So for example, pressure is going to be constant. Right? Now let HA is nothing but enthalpy of reactant A. HB is enthalpy of reactant B, right? Now let UA is equals to internal energy of reactant A, VAB, volume of reactant A, UBV, internal energy of product B, and VBB, volume of product B. Therefore we can write H is nothing but UA plus P VA, because pressure is going to remain constant, right? So let us write this down also, that P is the pressure of the system. Pressure of the system. So in that case we know that HA is going to be nothing but UA plus P VA, right? And HB is going to be UB plus PVB. Now delta H is going to be nothing but HB minus HA, which is going to be UB plus PVB minus UA plus PVA, which is going to be UB minus UA plus P into VB minus VA, right? Therefore this is delta H. Therefore we can write delta H is going to be nothing but delta H is going to be equal to delta U plus P delta V, right? Where delta U is going to be UB minus UA, change in internal energy, and VB and delta V is nothing but VB minus VA, change in volume. Right? The difference between delta H and delta U is not usually significant for solids and liquids. However, when the system is involved gases, the difference becomes significant. Right? Let us write this down. The difference between delta H and delta U, this is not V, this is U, is usually not significant for solids and liquids. However, when the system involves gases, in the system involve gases, the difference becomes significant. So now consider a chemical reaction taking place at constant temperature T and pressure P. Let VA is the total volume of the gaseous reactant and VB is the total volume of gaseous products, right? Whereas Na is the number of moles of gaseous reactant, and Nb is the number of moles of gaseous product. So we are still considering the reaction as A going to B, right? Now according to the ideal gas equation, we know that P into V is going to be nothing but nRT. Now for reactants, this is going to be P multiplied by VA is nothing but NaRTA at constant T and P. For products, it is going to be PVB is nothing but NBRT at constant T and P, right? So like I said, this is equation 1, equation 2. Now what we do is 2 minus 1, therefore PVB minus PVA is nothing but NBRT minus NART, right? Therefore P into VB minus VA is going to be NB minus NA into RT. Therefore we can write P delta V is going to be nothing but delta N RT, right? Just conclude delta N of gaseous molecule, right? Where delta N J is nothing but change in the number of gaseous moles of products and reactants, right? Yeah. And we know that delta U is going to be delta H is going to be nothing but delta U plus P delta V. Therefore delta H is going to be nothing but delta U plus delta NGRT, right? Thus energy change at constant pressure is going to be nothing but energy change at constant volume plus change in the number of gaseous moles multiplied by RT. Hence, this is very important. Delta H is nothing but delta U plus P delta V, and delta H for ideal gas is equal to delta U plus delta Ng RT. So these two are very important relations, right? Right. So in this class, what we have seen is we have seen about the correlation between delta H and delta U, and then we have also calculated that delta U is nothing but heat added or evolved during the system when the process is carried out at constant volume, whereas delta H is nothing but heat evolved or absorbed during the process when the process is carried out at constant pressure. Then we have also studied the relationship between delta H and delta U. We have found that delta H and delta U, the change, they are almost equal for gases, for liquids and solids, whereas there is a correlationship between delta H delta U when the gases are involved, and that is nothing but energy change, that is delta H is nothing but delta U plus change in number of moles of gaseous molecule, that is number of moles of products minus number of moles of reactant multiplied by the RT value, right? So in the next class, what we are going to study is we are going to solve some examples, and then we are going to study about the exothermic and endothermic reaction, and what are those, and then we may also further go into the another thermodynamic property called as the heat capacity. So heat capacity, there are also two types of heat capacity, that is heat capacity at constant volume and heat capacity at constant pressure. So we are going to study about it, and then we are going to quantify its physical meaning as well. So I thank you all for attending this class, and I hope to see you all again in the next class. Thank you.